Good day, esteemed researchers and viewers worldwide. We're excited to present our paper, Metric-Centered and Technology-Independent Architectural Views for Software Comprehension, by Luis F. Mendevelso, Heli Garces, and Ruby Casales. Our research tackles the challenge of understanding complex software programs, a task that consumes over half of all maintenance activity. We propose a novel approach that enhances flexibility and customization in building abstractions, thereby improving software comprehension. Stay tuned for intriguing insights and implications. Moving on to the key highlights of our research. Our work primarily addresses the significant challenge of understanding a program, which forms more than half of all maintenance activity. This task is made even more complex due to the absence of abstractions and applications, often comprising thousands of lines of code spread across hundreds of files. Additionally, the lack of documentation about the design further complicates the process. Our approach aims to tackle these issues, making program understanding more accessible and efficient. In this slide, we delve into the key problem our research aims to address. We're dealing with complex applications that have thousands of lines of code, scattered across hundreds of files. This complexity makes understanding these applications a daunting task, but the challenge doesn't stop there. We also face issues due to the lack of knowledge about the architectural decisions that were made during the original design of these applications. Over time, these decisions can degrade, and modifications and additions can further complicate the understanding process. Our research is focused on finding a solution to these problems, and we'll be discussing our approach in the upcoming slides. In this slide, we delve into the key insights of our approach. Firstly, our approach enhances program understanding by offering a more adaptable and customizable method for building abstractions. This flexibility allows for modifications to suit various source technologies, making it a versatile tool in the field of software visualization. Secondly, our approach strikes a balance between reusability and expressiveness. It does this by having a pivot for each family of technologies. This means that it can be easily adapted and reused across different technological contexts, while still maintaining its expressive power. Lastly, our approach empowers users to define new structural elements and corresponding metrics. This feature is particularly useful in facilitating software comprehension tasks, as it allows users to tailor the software visualization and modeling to their specific needs. This user-defined customization is a key strength of our approach, making it a valuable tool for software developers and researchers alike. In this slide, we delve into the key highlights of our research. Our primary contribution is an innovative approach based on model-driven reverse engineering, or MDRE. This approach allows us to annotate a platform-independent metamodel, or PIM, providing a flexible and adaptable tool for understanding complex software systems. Our approach is not limited to a single technology or framework. Instead, it's extensible, capable of adapting to a wide range of source application technologies and view specification frameworks. This flexibility makes it a versatile tool for a variety of software modernization projects. Additionally, our approach incorporates clustering algorithms. These algorithms group structural elements of the source applications, simplifying the process of understanding and maintaining large, complex software systems. In summary, our research presents a flexible, adaptable, and efficient approach to software understanding and maintenance, offering significant potential for future applications. In this slide, we delve into the key highlights of our approach. Firstly, we use annotations to help users specify the structural elements to be displayed and represent particular software metrics via the elements style. This innovative method allows for a more tailored and efficient visualization of software architecture. Secondly, our approach empowers users to define new structural elements needed for facilitating software comprehension tasks. This flexibility is crucial in the ever-evolving field of software development, where new challenges and requirements emerge regularly. These two main points underline the strength of our approach in providing a more user-friendly and adaptable tool for software visualization and comprehension. In this slide, we're going to highlight some key results from our research. Firstly, we applied our approach and tool in the concrete cases of Oracle Forms, Java EE, and Ruby on Rails. This allowed us to test the flexibility and adaptability of our solution across different technologies. Secondly, our evaluation was tailored to the specific needs of each project, ensuring a practical and relevant assessment of our approach. Lastly, we found that our approach was able to generalize what was originally done in a specific way for a particular project. This improved flexibility in the tasks of program understanding, demonstrating the potential of our solution to adapt to a variety of scenarios. These results underscore the versatility and practicality of our approach in real-world applications. Moving on to the introduction and problem setting, let's take a look at this figure. This diagram provides an overview of the process at the application or domain engineering level. Our approach was designed with two main requirements in mind. The first is software visualization, which is crucial for understanding complex software systems. The second is the modeling of software metrics that impact the views. This is important because it allows us to quantify and measure the impact of different factors on our software. In the next section, we will delve into related work that shares similar requirements to our approach. This will help us understand the context in which our work is situated and how it contributes to the broader field. Let's delve into the heart of the problem we're addressing. Picture an application, a vast landscape of code, thousands of lines, scattered across hundreds of files. It's like trying to navigate a city without a map. The absence of abstractions in these applications is the root of the complexity we face. This image here provides an overview of the process at the application or domain engineering level. It's a visual representation of the challenge we're tackling. We're trying to make sense of this intricate web. To understand the underlying structure and relationships, this is the problem setting we're working within. As we delve deeper into the problem, we encounter additional challenges that make understanding a program even more complex. One of these is the lack of documentation about the design. This absence of information can make it difficult to comprehend the structure and functionality of the program. Another challenge is the lack of knowledge about architectural decisions. This is often due to developer turnover, which can lead to a loss of crucial information about the program's design and structure. Lastly, the degradation of previously made decisions adds to the complexity. Over time, additions and modifications can distort the original design, making it harder to understand. As you can see in the figure, these challenges are part of the broader process at the application or domain engineering level. In this slide, we delve into the limitations of existing tools used for building abstractions. The current landscape of tools is heavily dependent on the language or technology they are designed for. This dependency restricts their flexibility and adaptability. Moreover, these tools are confined to predefined views, which may not necessarily align with the specific understanding needs of different projects. This graphic here provides an overview of the process at the application or domain engineering level, illustrating the complexity of the task at hand. As we move forward, we'll explore how our approach addresses these limitations, offering a more flexible and adaptable solution. Let's delve into the heart of our research. On the screen, you can see an overview of the process at the application or domain engineering level. This diagram illustrates the complexity of the task at hand. Now, why are we here? We've identified a pressing need for a new approach. The existing methods for understanding programs have their limitations and challenges. They often lack flexibility and customization, making it difficult to adapt to different technologies or specific user needs. Our goal is to address these issues and develop a more adaptable and user-friendly approach. This will not only enhance our understanding of programs, but also streamline the maintenance process. Stay tuned as we unravel our innovative approach. Let's delve into the heart of our proposed solution. We've developed an approach based on model-driven reverse engineering, or MDRE for short. This approach allows us to annotate a platform-independent metamodel, which we'll refer to as PIM. Now, what makes this approach truly unique is its extensibility. It can be applied to a wide range of source application technologies and view specification frameworks. This flexibility opens up a world of possibilities for understanding and maintaining complex software systems. The figure here provides an overview of the process at the application and domain engineering level, giving you a visual representation of how our approach works in practice. Let's delve deeper into the key features of our proposed method. As you can see in the figure, we have an overview of the process at the application or domain engineering level. Our approach includes the use of clustering algorithms. These algorithms group together structural elements of the source applications, simplifying the process of understanding the application structure. Moreover, we introduce the concept of annotations. These annotations serve a dual purpose. First, They help users specify which structural elements they want to be displayed. Second, they represent particular software metrics through the style of the elements. This means that the color, size, and labels of an element can give you insights into specific software metrics. In essence, our method provides a more intuitive and customizable way of visualizing and understanding complex software structures. Let's delve into the novelty of our proposed method. As you can see in the figure, we provide an overview of the process at the application and domain engineering level. The key improvement of our approach over existing methods is its flexibility. It allows users to define new structural elements that are crucial for understanding software. This means that instead of being limited by what's explicitly present in the source structure, users can create elements that facilitate their specific comprehension tasks. This innovation enhances the adaptability and effectiveness of our method, making it a valuable tool in the field of software visualization and metrics modeling. Moving on to our related work section, we delve into the landscape of existing approaches. These approaches are versatile, capable of taking inputs from various technologies. They also have the ability to reflect software metrics in views. This is a crucial aspect as it directly impacts the visualization of software. However, our approach is unique in its design, specifically tailored to meet two main requirements: software visualization and modeling of software metrics. This makes our approach distinct and potentially more effective in certain scenarios. We'll explore this further as we progress. In this slide, we delve into the limitations of existing approaches in the field of software visualization and metrics modeling. Firstly, these approaches often transform source artifacts to a unique pivot. This can lead to a loss of direct correspondences between the source technology and the intermediate representation, making it difficult for others to understand. Secondly, the elements and metrics displayed in the view are limited to those explicit in the source structure. This restricts the user's ability to define new structural elements needed for facilitating software comprehension tasks. Lastly, these approaches render views and editors under a fixed technology, limiting their adaptability to different views specification frameworks. These limitations highlight the need for a more flexible and comprehensive approach, which we aim to address in our work. Moving on to our comparison with the closest related work, we find some similarities and key differences. Both our approach and the related work can handle input from various technologies and reflect software metrics in the views. However, our approach stands out in several ways. Firstly, we use a unique pivot for each family of technologies, which reduces the risk of losing direct correspondences. Secondly, our approach empowers users to define new structural elements that facilitate software comprehension tasks. Lastly, unlike the related work that is limited to the Sirius framework, our approach can map to different views, specification frameworks. This flexibility allows us to cater to a wider range of needs and preferences. Let's delve deeper into our proposed method. As we know, understanding a program forms a significant chunk of maintenance activity. However, the lack of abstractions in applications often complicates this process. Existing tools that help build these abstractions are often tied to a specific language or technology, and may not cater to unique understanding needs. The figure you see here provides an overview of our process at the application or domain engineering level. Our method aims to address these challenges, making program understanding more efficient and effective. In this slide, we delve into the technical details of our proposed research. The figure you see provides an overview of the process at the application or domain engineering level. Our approach is rooted in model-driven reverse engineering, or MDRE. This method allows us to annotate a platform-independent metamodel, or PIM, which is a key aspect of our approach. One of the significant advantages of our approach is its extensibility. It can be applied to a wide range of source application technologies and view specification frameworks. This is a departure from existing methods, which are often limited to a unique pivot. In essence, our approach provides a more flexible and adaptable solution for understanding complex software systems. It's about making the process of software comprehension more efficient and effective, regardless of the technology or framework being used. Let's delve deeper into the technical aspects of our proposed method. As you can see in the figure, we have an overview of the process at the application or domain engineering level. Now, let's highlight some key features of our approach. Firstly, we use clustering algorithms to group structural elements of the source applications. This helps in simplifying the complex structure of the software. Secondly, we use annotations to help users specify the structural elements to be displayed. These annotations also represent particular software metrics via the element style. Lastly, our approach is designed to be flexible. It allows users to define new structural elements that are not present in the source structure, but are needed for facilitating software comprehension tasks. These features together make our approach a powerful tool for software visualization and understanding. On this slide, we delve into the technical details of our proposed method. This approach sets itself apart from others by having a unique pivot for each family of technologies. This not only allows for a high degree of customization, as users can define new structural elements, but also ensures compatibility with different view specification frameworks. The key to our approach is striking a balance between reusability and expressiveness, which we achieve by having a unique pivot for each technology family. This diagram provides an overview of the process at the application or domain engineering level. As we move forward, we'll see how these elements come together to create a comprehensive and adaptable solution. On this slide, we delve into the technical details of our research. The figure you see provides an overview of the process at the application and domain engineering level. Now, let's talk about the evaluation of our proposed method. We applied our approach and tool in 3 distinct cases: Oracle Forms, Java EE, and Ruby on Rails. What we found was that our approach was able to generalize what was originally done in a specific way for a particular project. This resulted in a significant improvement in flexibility when it comes to understanding programs. This is a crucial step forward in our field, as it allows for greater adaptability and efficiency in software development. On this slide, we delve into the technical results of our approach. As you can see in the figure, we've obtained views for applications developed under 3 different technologies: Oracle Forms, Java EE, and Ruby on Rails. This demonstrates the versatility and adaptability of our approach. Our method excels in generalizing specific project tasks, which enhances flexibility in program understanding. It's unique in that it provides a pivot for each family of technologies, allowing user-defined structural elements and mapping to different views specification frameworks. This approach not only enhances program understanding by providing flexible and customizable abstractions, but also strikes a balance between reusability and expressiveness. It empowers users to define new structural elements and corresponding metrics, facilitating software comprehension tasks. In essence, our approach is designed to be adaptable, flexible, and user-friendly, catering to a wide range of technologies and user needs. Begin a frame title: flexibility and adaptability. Begin mini page, T 0.5 line width. Begin itemize, item figure. Demonstration of our approach's flexibility across different technologies. Item section 3. Evaluation of flexibility. Begin itemize. Item: our approach's flexibility is its key strength, allowing it to be easily modified for use across various source technologies. Item: we've tested this on Oracle Forms, Java, and Ruby, which are quite different from each other, demonstrating its wide applicability. Item: the results from these industrial cases show that our approach can be successfully applied to a diverse range of technologies. Item: this adaptability makes our approach a powerful tool for software comprehension in the industry. End itemize, end mini page, hfill, begin mini page. T is 0.5 line width. Begin a figure. Centering. Include graphics. Height equals 0.8 text height /src /task _execution /extracted _paper _data /171529166569 S40411-018-0060-6 figure /171529166569 S40411-018-0060-6 figure 7-1.png. End of figure, end of mini page, end of frame, .. In conclusion, this paper introduces a unique approach that leverages model-driven reverse engineering, or MDRE, to enhance our understanding of programs. This method is versatile, capable of extending to a variety of source application technologies and view specification frameworks. It incorporates clustering algorithms and annotations, which aid users in specifying the structural elements they wish to display. Moreover, Our approach empowers users to define new structural elements, facilitating their software comprehension tasks. We've applied this method to Oracle Forms, Java EE, and Ruby on Rails, and found that it can effectively generalize solutions across different projects. What sets our approach apart from others is its use of a pivot for each family of technologies, its ability to allow users to define new structural elements, and its capacity to map to different views specification frameworks. This makes our approach both flexible and adaptable, catering to a wide range of needs and applications.